Ladies and gentlemen, good afternoon. This is the February 11th, 2017. This presentation is organized in DCU Adapt. And today the theme of the topic is the multi-view learnings. And the title is Learning Multiple Views with Orthogonal Denoising Autoencoders. So the task is learning multiple views, and the model is Orthogonal Denoising Autoencoders. So first, this is the whole structure of this presentation. The first, I will try to illustrate what is multi-view learning, which means if you need to use it, you have to know when you should use it. And then I will talk about this model, that is how you use this model to solve this problem. And then I will show my experiments, including some codes. So multi-view learning, it is a very general topic. It is an umbrella term, which means it can fit a universal situation. For example, this word hello, it has in different languages, it has different versions. So each version is a different view of this semantic meaning. And another example is the video. So the video consists of the visual part and the sounds. So each part, you have to combine it, it will become a whole. Another example, like in real world, it is like 3D world, but if you see in a screen, you can only see the two dimensions. So that is aspects, and we also call it a view. So as you can see, a lot of scenarios in real world, we will call it a view. So what exactly are views? Views are multiple disjoint feature sets. For example, the examples like we talked about, the videos, the visual parts, they consist of the pixels. Well, the sounds, they are like the magnificent, like the waves. So those features are different, and you can easily tell them apart. And also for the web HTML, it has both the images and text, the words, and you can also easily distinguish them. So the feature sets, like images, like sounds, they are different. But for each view, it may have more than one feature. So the descriptors or the sensors like the videos, you take photos and the sound, they are from different sensors, so they are essentially different. And the descriptors, like you have for the same word, the same semantic meaning, you have different descriptors. And for the same object, you have its different aspects, different views. Those are the two main reasons that will cause the multi-view. And this word has high occurrence in different fields. Like in multimedia, we call it the multimedia fusion. And in data mining, we call it the modality combination. And in machine learning, we'll call it just multi-view learning. So because I mainly studied the machine learning, so I will use this multi-view learning as the basic term. So how this problem appears? Because a very intuitive solution is like we could just combine all these features together and consider them as a whole, and then we apply those classifiers to solve the problem. But as you may feel that, because if we combine them together, the dimensions will be quite high, so it will easy to go overfit. And on the other hand, the reason behind that is for each view we have a lot of redundant information. For example, like just the text, the HTML example. We may have like the images and the text. The images, the information are redundant because maybe after we read the text, we'll already know what the author is going to tell us. Or either way, we could just read to see the images, and the reason also applies for this example. So, as you can see, the information is redundant, and so, but also we cannot just use only one view, like one only set of features, because like those informations were discarded by one view, maybe retained by others. Like if you just watch these videos, if you just listen to the sound, you may lose a lot of information for sure. No one will go to the cinema and just listen to the films. So after a long history, researchers have concluded 2 principles for those problems. The first is consensus, and the second one is complementary. Consensus, it considers like, so a lot of information is redundant, but they are consistent. Like if you watch a film, no matter you listen to a sound or watch the subtitles or watch the images, the visual information, visual stream itself, it all express the same information. And on the other hand, those information will complement each other. Like for example, like maybe there is no sound in a section of the film, but also it has some actors, and there are some movements of the actors and some facial expression. There are also information, right? So those 2 principles are based on those. So the consensus, they will try to maximize the agreement, which means like they want the information between different views to be consistent as possible, while the complementary principle wants the private information to correct the errors for the other. So now there are 3 approaches based on the 2 principles. The first is the co-chaining. Co-chaining, like for example, you have the first view, you have the second view. So the first step is you use the information from first view to train the model, and then you predict the information like for the labels for the second view, and then you combine that to train a more model. It is like more iterative way to improve the performance. And the second way is the multiple view kernel learning. Like this idea comes from the SVM. As you know, the SVM is brings up a lot of result. One is the kernels. So for each view, we will use the kernels to represent. It is a representation to represent those information. And those kernels, in kernel learning, it is easily to combine different kernels, so they will regard it as a whole. But as far as I know, the computation is quite complex. And third way, subspace learning. So we regard views from different latent subspace. So we see like the whole thing, it is like a space, and different views are different subspaces, and in that way we try to make them orthogonal, because as long as it is orthogonal, the redundant information will disappear, and we will remove a lot of redundancy, and that's the reason. So okay. So far, you know what is multi-view learning. You know like the history of it. And next, I'm going to tell the model. So before that, I'm going to give you some prior knowledge about the representation learning in case somebody is unfamiliar with that. So autoencoders is a kind of one hidden layer neural network, and it has a narrow hidden layer. So the hidden layer will render the compact representation. And denoising is because although the representation is compact, but denoising will enable it to be more robust. And orthogonal is especially for the multiple view. So the model is called the Orthogonal Denoising Autoencoders. And by the way, if I remember right, the denoising is proposed by the Banjo in 2008 or 2009. So this is how does the model look like. It is different from traditional autoencoder.
Sorry, you mean Yoshio Banjo?
Yeah.
Oh.
Yeah, that Banjo.
Yeah. That's a big guy.
Yeah. So as you can see, like basically it has similar part to the autoencoders. It has a very narrow hidden layer part and wide input and output. So for the autoencoder, the input and output should be the same size. But the different thing is like the fully connection is disconnect in order to make orthogonal. So this is the first view, and this is the second view, because views are set of the sets of features. So as you can imagine, if you have a matrix, if you put your data into a matrix, and the lines, the rows are the features, and the columns are the examples. Example 1, example 2, example 3, and features 1, features 2, features 3. So you can just put them here, the first view, the second view. And then just to notice, like for the first view, it only connects to the shear space, and the private space is this one. And for the second view, similar, connects to the shear space and the second neural of the private spaces. So in summary, in shear space, well, in real cases, the number of neurons may be more than one. So it may be 2, 3, or more parts. So in shear spaces, all the neurons will have fully connected with the private one, with the input. But in private spaces, they only connect to their own part. If you are belongs to the first view, then we connect to only the first view. If you have only the second view, we only connect to the second view. So it is not fully connected, and similar to those. In this way, okay. So what do we want? So we want a representation. This is representation, and we also want the representation of the private spaces to be orthogonal. Okay, then let me show you how does the model do it. So private spaces are independent. So those parts are independent. The information are independent. So suppose like this is the input, and this is for the first view, and this is for the second view. View 1, view 2, and this is the weight of the of this. This is weight of this. Disconnect, because those are for the second view, and those for the first view. And when you apply it, orthogonal, right? Because if you multiply them, orthogonal. So private spaces are independent. So we want them to be independent. And now what I'm going to prove is like the shared space. This is also orthogonal to the private spaces. So assume that you have the same information from view 2. I'm going to show you it will go through this way, not that way. So in order to improve this, let's assume that it will also go to this way. So we don't want it to go through the red lines because we don't want the private information to go to the shared space. Okay, so and then we assume it goes to it, and then the information from the shared space will feed forward to both the first view and second view because it is connected. And then what? And then because this is autoencoder, the autoencoder wants the input to be as close as output, but then the information from the second view goes to the first view. So those are what are those? Those information are noises to the first view. It will increase the error. So normally we'll use the square error loss function or odd function. So those are noises because those are private information. Just to recall, like what we want from the this model. First of all, we want this to be representation. Second, remember our two principles. Both views have some information which is consistent, and they have all their own private information. We want their public information or shared information go to this way, and we want their private information to go this way. So those information will be independent, which is orthogonal. So I just proved that the information here is independent of private space. The shared space is independent of private spaces. So their shared information, their public information will go to this way. And I also proved that for each of them, their private information, they are independent. So in this way. This may be hard to understand, but we will discuss it later, like in later time. In my previous presentations, a lot of people are confused about it, like how is like in private spaces the information is independent, because it is like assume it will happen, and we prove if it happens, it will increase the error, the loss. So the chaining is simple because we just disconnect set the disconnection to 0, and that's all. The back propagation still applies. And then how to use it? So those are the experiments. So these are synthetic data. So as you can see, like the red lines are public information, and the green lines and white are the private information. So there are two views, and for both of view, the common information is red lines, and the private information is blue line and red line. It doesn't matter which belongs to which. So this is a synthetic data. So we use those data to create the 21 dimensions of views. So this is the first view, this is second view, and each view have 21 dimensions. And those dimensions data are combination of those signals. So our task is inverse, trying to use the model to extract those information, the signals. So this is from the canonical correlated analysis, a very classical statistical method. As you can see, like it can only extract the only two signals. But in my method, it can extract the red line, blue line, green line, this is non-denoising, this is denoising. As you can see, like some people may ask, like the red lines should be like more small, like it is not totally the same. As I mentioned, that this is a very good question, but just if you go back to the model, so in your network, if you put the weights and those, at least the signal is like the scaling. So it should be like this, but the signals will go scaling in the inverse way. So it will amplify, the red lines amplify, but that is fine, because if you do the extraction, you only want to know the representation. You don't care like if the pixel is 0.8 or like in which units. So a real world experiment is using the Pascal VOC, and I use both the images and texture annotation. So sorry. So I did 20 experiments, and it wants like 7 champions and 10 runner-ups. So as you can see, the advantages is elegant, it is easy, and it is practical. But drawback is same as neural networks. You have to tune, hyperparameters tune. It takes a lot of work. So I put the code here. Yeah. So as you can see, the code is here. I manually implement the neural network and feed-forward, backpropagation, and stochastic gradient descent. And so you can easily to change the code to adapt to your own requirement. This is the stochastic gradient descent, and yeah. So
cool.
We stop here and take some rest.
Yeah, we can. Yeah. Thanks.